This lecture is going to be over sections 30.5 to 30.7. So a nuclear reaction is going to be the result of a bombardment of a nucleus by a particle rather than a spontaneous natural process like with radioactive decay. For charged particles such as a proton or an alpha particle to penetrate the nucleus of another atom, it must usually have enough initial kinetic energy to overcome the potential energy barrier caused by the repulsive electrostatic forces. Nuclear fission is a decay process in which an unstable nucleus splits into two fragments. The total mass of the resulting fragments is less than the mass of the original atom. And this released mass energy appears mostly as kinetic energy of the fragments. In a nuclear fusion reaction, two or more small light nuclei come together to fuse to form a larger nucleus. Fusion reactions release energy for the same reason as fission reactions. The binding energy per nucleon is greater after the reaction than before it. Okay. So earlier this chapter, we studied the decay of unstable nuclei by the spontaneous emission of an alpha or beta particle, sometimes followed by gamma emission. Nothing was done to initiate this emission, and nothing could be done to control it. In other words, it just happens. But some other processes in which nuclear particles are rearranged as a result of the bombardment of a nucleus by a particle, rather than some sort of spontaneous natural process, is what we're going to be looking at. Ernest Rutherford suggested in 1919 that a massive particle with sufficient kinetic energy might be able to penetrate a nucleus. The result would be either a new nucleus with a higher atomic number and mass number, or a decay of the original nucleus. Rutherford bombarded nitrogen with alpha particles from naturally radioactive sources and obtained an oxygen nucleus and a proton, according to this equation. This process is called a nuclear reaction. Nuclear reactions obey the classical conservation principles for electric charge, momentum, angular momentum, and energy. In other words, they're not exempted from any of those. Another conservation law, not anticipated by classical physics, is conservation of the total number of nucleons. The number of protons and neutrons need not be conserved separately. In other words, the total number is conserved, but the numbers of the individual types of particles can vary. So when two nuclei interact, charge conservation requires the sum of the initial atomic numbers to be equal to the sum of the final atomic numbers. For conservation of the total number of nucleons, the sum of the initial mass number is also equal to the sum of the final mass numbers. But the initial rest mass in general is not equal to the final rest mass, reflecting the fact that collisions may be inelastic. So the difference between the rest masses before and after the reaction correspond to the reaction energy, according to the mass energy relationship here. If mass particles A and B interact to produce final particles C and D, then the reaction energy is defined as follows. To balance the electrons, we use the neutral atomic mass in equation 30.12. In other words, this for proton, this for helium, and so on. So when Q is positive, the total mass decreases and the total kinetic energy increases. This is considered to be exoergic, or borrowing from chemistry, an exothermic reaction. When Q is negative, the mass increases and the kinetic energy decreases, and is considered to be endoergic or endothermic. Notice that an endoergic reaction cannot occur at all unless the initial kinetic energy is at least as great as Q. This is called the threshold energy of the reaction. So you've got several problems there that you can kind of work through. So let's go back up here. Nuclear fission is a decay process in which an unstable nucleus splits into two fragments of comparable mass instead of emitting an alpha or beta particle. It was discovered in 1939 when Otto Hahn and Fritz Strassmann bombarded uranium with neutrons. The resulting radiation did not coincide with any known radioactive nuclei. Meticulous chemical analysis led to the astonishing conclusion that they had found a radioactive isotope of barium and krypton. So then they concluded that the uranium nuclei was splitting into two massive fragments, which they called fission fragments. A few free neutrons usually appeared along with the fission fragments. The energy released during fission, almost 200 MeV per nucleus, emerged as kinetic energy of the fission fragments. So both the common isotope U-238 and U-235, as well as other nuclides, can be split by neutron bombardment. This by slow neutrons, but U-238 only by neutrons with at least 1.2 MeV of energy. Fission resulting from nuclear absorption is called induced fission. Some nuclei can also undergo spontaneous fission, in which you don't need the initial neutron absorption. More than 100 different nuclei representing more than 20 different elements have been found among the fission products. And you can see here in this figure where it shows the distribution of mass numbers from fission fragments from nuclide 235. Fission reactions are always exergic because the fission fragments have greater binding energy per nucleon than the original. The total kinetic energy of the fission fragments is enormous, about 200 MeV. Fission fragments always have too many neutrons to be stable. The N/Z value for the stable nuclides is about 1.3 at A is equal to 100 and about 1.4 at A is equal to 150. The fragments have approximately the same N/Z as U-235, about 1.55, and they respond to the surplus of neutrons by emitting 2 or 3 free neutrons and by undergoing a series of beta decays, beta minus decays. So fission of a uranium nucleus triggered by nuclear bombardment releases other neutrons that can trigger more fissions, thus a chain reaction is possible. The reaction can be made to proceed slowly and in a controlled manner, like in a nuclear reactor, or not quite so slowly as in a bomb. The energy released in a chain reaction is enormous, far greater than any chemical reaction. So for example, when uranium is oxidized or burned to uranium dioxide, the heat of combustion is about 4,500 joules per gram. Expressed as energy per atom, it's about 11 eV per uranium atom. By contrast, fission liberates about 200 MeV per atom, or 20 million times as much energy. So you can see here, you've got a neutron coming in, hits one of these nuclei, you've got the krypton and the barium being released, you've got another lost neutron going around, boop, boop, they hit another one, and you get some more products coming out, boop, boop, and then these neutrons go out again, and then you create more stuff, and things just keep going on forever. Well, not quite forever. A nuclear reactor is a system in which a controlled nuclear chain reaction is used to liberate energy. In this plant, this energy is used to create steam, which operates a turbine and then turns an electrical generator. On average, each fission of a U-235 nucleus produces about 2.5 free neutrons, so 40% of the neutrons are needed to sustain a chain reaction. The probability of neutron absorption by a nucleus is much greater for low energy than for higher energy. The emitted neutrons are slowed by the collisions with nuclei in the surrounding material called the moderator, so they can cause further fissions. In nuclear power plants, the moderator is often water, occasionally graphite. The rate of reaction is controlled by inserting or withdrawing control rods made of elements called often cadmium, whose nuclei absorb neutrons without undergoing any additional reaction. So the isotope U-238 can also absorb neutrons, leading to U-239, but not with high enough probability for it to sustain a chain reaction by itself. Thus, uranium used in reactors is enriched by increasing the proportion of 235 from the natural value of 0.7, typically to 3, by an isotope separation process. So in a nuclear plant, the fission energy appears as kinetic energy of the fission fragments, and the immediate result is to heat the fuel elements and the surrounding water. This heat generates steam to drive turbines, which in turn drive the electrical generators. Steam generator is a heat exchanger that takes heat from this highly radioactive water and generates non-radioactive steam to run the turbines. So you've got the control rods, you've got your moderator here, you've got the hot water that comes out, generating steam, and then goes back through the circulation process. The steam goes through here, turns a turbine. And then you can see as it goes on into the generator, generating electric power. And then you can see the steam as it goes through here, the coolant coming in, condensing the steam, and then the water coming back through this way. So you can see a circulation of water within here, and then you can see water circulating through here, water going to steam and then back again. And a typical nuclear power plant has an electric generating capacity of about 1,000 megawatts. The turbines are heat engines and are subject to the efficiency limitations imposed by the second law of thermodynamics. In modern nuclear power plants, the overall efficiency is about 1/3, so about 3,000 megawatts of thermal power from the fission reaction is needed to generate 1,000 megawatts of electric power. So in a nuclear fusion reaction, two or small lighter nuclei come together to form a larger nucleus. And fusion reactions release energy for the same reason as fission reactions. The binding energy per nucleon after the reaction is greater than that before. So referring back to this figure, we can see that the binding energy per nucleon increases with A up to about 60. So fusion of nearly any two light nuclei to make a nucleus less than 60 is likely to be exoergic. Here are three examples of energy liberating reactions. You've got hydrogens coming together to produce helium, hydrogen, and I believe, let's see, deuteron. That's what I was looking for. I don't know why they've got that flip there. To produce helium, and then you've got two helium atoms coming together to produce ordinary helium, as well as two protons. So the positrons produced during the first step collide with the electrons, mutual annihilation takes place, and energy is converted into gamma radiation. The net effect of the sequence is therefore the combination of 4 hydrogen nuclei into a helium nucleus and gamma radiation. The net energy release, which can be calculated from mass balance, turns out to be 26.7 MeV. These fusion reactions, known as the proton-proton chain, take place in the interior of the sun and other stars. Each gram of the sun's mass contains about this number of protons. It's a lot. If all of these protons were fused in the helium, the energy release would be about 130,000 kilowatt hours. If the sun were to continue to radiate at its present rate, it would take about 75 billion years to exhaust its supply of protons. For two nuclei to fuse, they must come together within the range of the nuclear force. To do this, they must overcome the electrical repulsion of the positive charges. For two protons, a distance of this apart, the corresponding potential energy on the order of this, or 0.7 MeV. This amount represents the initial kinetic energy the fusion nuclei must have. And these are available at extremely high temperatures. The average translational kinetic energy of a gas molecule, temperature T, is this, where K is the Boltzmann's constant. For this energy to be equal to this, the temperature must be on the order of this. And not all nuclei have to have this energy, but the temperature must be on the order of millions of kelvins if any appreciable fraction of the nuclei are to have enough kinetic energy to surmount the electrical repulsion. Fusion chain reaction with such high temperatures occur in the interior of stars. Because of these extreme temperature requirements, such reactions are called thermonuclear reactions. An uncontrolled thermonuclear reaction occurs in a hydrogen bomb. That's pretty bad. There are years of intensive efforts in laboratories around the world to achieve controlled fusion reactions, which potentially represent an enormous new energy resource. In one kind of an experiment, a plasma is heated to an extremely high temperature by electric discharge while being contained by appropriately shaped magnetic fields. In another experiment, pellets of the material to be fused are heated by high intensity laser beam. As of yet, no one has succeeded in producing fusion reactions under controlled conditions to yield a net surplus of usable energy.